Hello, I'm Dr. Kathleen Schmidt from Lawrence Livermore National Laboratory. Welcome to the Data Science Institute's virtual seminar series. With Lawrence Livermore being home to many challenging data sets, as well as some of the world's most advanced supercomputers, data science has become an essential discipline in the lab's key program areas. The DSI acts as a central hub for the lab's data science activities by fostering collaborations, promoting research, and engaging in outreach activities. Our DSI staff work in a variety of areas, including artificial intelligence, big data analytics, computer vision, machine learning, predictive modeling, statistical inference, and uncertainty quantification. The DSI hosts events like this seminar series to introduce new ideas and potential collaborators to the lab. We invite speakers from other institutions, both from the Bay Area and beyond, to share their innovative projects, approaches, and ideas with our data science community. We're pleased now to include a wider audience beyond the lab to engage with us through this series. You can read about past speakers on our website, data-science.llnl.gov, or email us at datascience@llnl.gov. Thank you, and enjoy the seminar. For this seminar, we have Brendan Peterson, who is a well-known part of LLNL's data science community. He's been at the lab for nearly 5 years and currently leads the operations research and systems analysis group. The work that he's presenting today is from a symbolic regression paper that was accepted for an oral presentation at this year's International Conference on Learning Representations. And this is particularly impressive because the acceptance rate for oral presentations is about 1.5%. So big congratulations to Brendan and his team, and I'll now turn it over to Brendan so we can hear more.
Thank you, Katie. Thanks everyone for joining. Today I'll be talking about deep symbolic regression. It's a method that we have to discover mathematical expressions from data via a novel approach called risk-seeking policy gradients. So this is joint effort in an LDRD at the lab with several others as shown here. And I also got one question already that said, "Hi, Dad." So I just wanted to say hi, Violet and Ellie, for watching. So I will go ahead and get started. So a lot of problems in machine learning are falling into this category that we call discrete sequence optimization. So it's kind of a mouthful mathematically, but the idea is that we want to optimize a sequence of discrete tokens, where tokens can be anything depending on the problem. We want to optimize them under some black box reward function. So if you look, we're taking the argmax over a reward, and this reward is a function of this tau1 through tau n. These tau1 through tau n are mathematical building or discrete building blocks, and together they form a sequence. So in each member in the sequence is selected from a library of possible tokens, and we're trying to optimize this sequence under some black box reward. Black box meaning we don't have any gradient information, and the length of the sequence is a variable. So this is very abstract, but it's a very challenging problem just in the general sense, because the size of the search space is huge. It grows exponentially with the length of the sequence. So the search space scales as the number of tokens you have raised to the power of the maximum length. So just as a cross-reference, there's 10 to the 80 atoms in the universe, and it's pretty easy to construct a problem that quickly approaches that number. So again, that's very abstract. So we'll get a little bit more concrete into the possible problem instances that fall into this category. One of them that's very popular right now is called neural architecture search. So this is the task of trying to search the space of neural network architectures. You're trying to optimize the best architecture, not the weights of the network, but the actual architecture itself. So things like which activation functions to use, how many layers, what's the width of each layer. So in this case, the library of tokens would be things like ReLU or Tanch activation, 32 or 64 nodes per layer. And then the reward would be given some string of architectural hyperparameters. You instantiate that neural network, you train it on some downstream ML task that you care about, and you take the validation accuracy, just a single scalar, and that's the reward. So computing the reward in this case has some inner optimization loop where you're actually training the neural network. Another completely different problem would be antibody design. Say you're trying to design a particular antibody that binds closely with a reference compound. So in this case, your library would be the set of 20 different amino acids. And you're constructing each token or amino acid as a sequence that corresponds to an antibody or some small region of an antibody. And then your reward is the binding affinity of that specified antibody to some reference compound. And we're trying to optimize for binding affinity. Third is a problem called symbolic regression, which will be the focus of this talk. So symbolic regression is a problem where essentially you're trying to fit mathematical equations to data. So I'll describe it more in the next slide, but here's just a very high level to show that, even though we're focusing on the symbolic regression task, the methods we'll discuss actually apply to any of these problems. So symbolic regression is a neat little, not super well-known problem in machine learning, where you're given a data set of XY pairs, and you're just trying to find a mathematical expression that fits the data well. So the task sounds a lot like regular regression, but there's one key difference. The main thing is that in conventional regression, the model, the structure of the model is fixed, and it's posited a priori by the user. So the user says, I want to fit a linear model, or I want to fit a neural network model. That's a design choice, and then they train it by learning the parameters of that model. In symbolic regression, we're actually exploring the space of models and model structures. And those models might have parameters that we also need to learn, but the key idea is that we're searching the space. So models are these discrete entities, and so that's why it's really more of a discrete search than conventional regression, which is just parameter fitting, typically continuous variables. And in particular, the space of models that we generally want to consider is short mathematical expressions, because the idea is that what we really want is we want to learn something about our data, and we can learn something by fitting small mathematical expressions that help explain the data. So in physics, for example, this is very useful because it can give us insights into the relationships between input-output variables just by inspecting the expressions that we get. So symbolic regression is a very important problem, especially in physics, because it actually teaches us something new about the data instead of just fitting some black box to it. But there's also a lot of benefits of symbolic regression just as a testbed problem for the larger, more general problem of discrete sequence optimization. The first reason is because there's lots of community-vetted benchmark problems in symbolic regression. These are problems that the community has come up with, and there's lots of different papers and publications that are trying to approach these problems. So you have lots of literature data you can compare to. There's also a lot of strong existing baselines. Typically, they're evolutionary approaches like genetic programming. So we can compare to a lot of old approaches. And the last point is that the reward function for symbolic regression is very cheap computationally compared to, say, neural architecture search or antibody design. So for neural architecture search, just to compute one reward, you have to instantiate your network and you have to train it on some machine learning task and report back a validation accuracy. So there's a sort of inner optimization loop where you have to actually train a whole network. And for antibody design, well, you either have to synthesize an antibody in the lab, or more realistically, you would use some sort of simulation to estimate the binding affinity, but these biological simulations are often very expensive. So the reward for both of those cases is very expensive, whereas for symbolic regression, it's actually dirt cheap. So we output some mathematical expression. All we have to do is feed that expression our input data, and now we have predicted values. And we compare it to the real values with some mean squared error like reward, and there we have our reward. So it takes about a microsecond to compute the reward instead of minutes or hours. So the reason I'm dwelling on this point is because not just because it makes our lives easier, but it really lets us focus our human effort and get through a lot more human iterations and focus on the discrete search itself. So this is a symbolic regression project, but really the methods are aimed at improving discrete sequence optimization through reinforcement learning. In the more expensive fields like neural architecture search, it's well known that it's a difficult task to even just evaluate how good the search phase was. So there's a lot of very problem-specific issues that they have to deal with. Whereas in symbolic regression, we can run all of our problems 100 times, compute mean, standard deviation, statistical significance quite easily, and that's really just thanks to the fact that it's very cheap. So just as a little bit of background, one thing that we can do is we can take any mathematical expression and we can represent that as a tree, and then we can also represent that tree as a sequence. And I'll describe why that's important in a minute, but just to show how that works, we take an expression, this one, sine x divided by log of x squared, and we can convert this to what's called an algebraic expression tree. And this tree is composed of nodes that correspond to operators, and the children of those nodes are the operands. So the root node in the tree is essentially the outermost operation of the expression. So in this case, the outermost operation is division. So that's the root node of the tree. And the left subtree is the numerator, whereas the right subtree is the denominator. And from the tree, we can traverse this tree in a particular way. Namely, we use the pre-order traversal, which is a depth first, then left to right traversal. And we can traverse this tree to turn it into a sequence. And a key insight is that we maintain a one-to-one correspondence between this tree and sequence. And if you're familiar with graph theory, you'll know that that's actually not true in general. There's a loss of information going from tree to sequence, so you usually can't go back. But in this case, there's a special quality of the problem, which is that just given the node value, for example, sine or division, I know how many children it has. So sine is always a unary operator, so it always has one child. X is always an input variable, so it's always a terminal. And plus, minus, multiply, divide, those are all binary, so they all have two children. And it turns out that the combination of the traversal and the number of children that each token has is sufficient to reconstruct the tree. So we maintain this one-to-one correspondence between tree and sequence. So why is all that important? Well, the reason it's important is because now we can search the space of sequences, which is something that's a lot easier to do than search the space of trees when we still maintain this correspondence. In particular, we can generate expressions sequentially via recurrent neural network, which is where the deep learning aspect of this approach comes in. So that's what I'll describe in this slide. So this is really the sort of core aspect of the work, is that we generate expressions from a recurrent neural network. And we do this in a stochastic way. And then we'll go back, and the next question will be, how do we optimize this RNN to produce better expressions? But first, just sort of the mechanics of how do we generate expressions from an RNN. So we do this sequentially from left to right of the pre-order traversal, which means top down of the tree. So the very first thing we do is we draw this dotted circle, and we're trying to select this first node, which is the root of the tree. So we have a recurrent network. We first feed it with just these empty placeholder tokens, and the RNN outputs a categorical distribution. What we mean by that is that it outputs a vector of real numbers. We push that through a softmax, and the corresponding values correspond to the probability of selecting each token in a given library. So here we have this library of these 11 different tokens. So we have 11 different atoms in our categorical distribution, and from there we just sample. So we take one sample from this categorical. Let's say we get division. So now back on the right, we fill in that first node with the division operator. We know that division is a binary operator, so it has two children. And following the depth first, left, right, pre-order traversal, now we're selecting the second node on the left. Since it's a recurrent neural network, it updates its internal weights, and we also feed it the token that we just sampled, and now it outputs a different categorical distribution. We sample from that. Let's say we get sine, so we fill in sine. Sine is unary, so it has one child, and we just keep going until the expression is complete. So now there's one more unselected node. We select log, so there's again one more because it's unary. And finally, when we select terminal operator, the expression ends. So unlike natural language processing or things like that, there's no stop token or anything. The expression ends when the expression ends. That is when there's no more dotted circles, essentially, when all of the unselected nodes are filled in by terminal tokens, which would be the input variables or constants. So that's just what I'm showing is just one single forward pass through the RNN. If we were to do this again, we would get a completely different sequence that would correspond to a completely different tree, even with a different length, a different structure of the tree. And one other minor detail is that typically in these setups, you feed the token that you just sampled as the input to the next RNN. In our case, just to provide a little bit more context about the hierarchical nature of our underlying discrete object, we feed both the parent and the sibling token as input. So for example, before we choose this X, the parent is multiply and the sibling is a constant. So those are the inputs that we feed in before the RNN outputs the distribution. So this is really the core of our generator. And now from here on, the question is really, how can we optimize this? And again, in this example, the expression looks like this. And the pre-order traversal is just the sequence of tokens that we've sampled. So one other really cool thing that we can do with this approach, and it's really what sets us apart from competing approaches like evolutionary approaches, is that we can incorporate domain knowledge in a very efficient and straightforward way. So let's take the example from the previous slide and back up a bit. So let's say that we've sampled so far division and sign, and now we're sampling the child of the sign operator. Now, I'll zoom in really quick to these logits, which again, you can see correspond to the probabilities of selecting the different tokens in the library. Now, let's incorporate some domain knowledge. Let's posit that I don't want trig functions to be descendants of other trig functions. So you can't have, I want to say that we can't do, sine of cosine of x or sine of 1 plus tangent or anything like that. Because, while that might be semantically meaningful, nested trig operators isn't really something that you see in the wild. So this is just an example of a constraint that we can impose. And the way you do it is actually really simple. Before you sample anything, you feed it through all of your constraints and say, well, would choosing any of these violate a constraint? And if so, all you do is zero out the probability of choosing them. So you just adjust the probabilities directly. And this is also taken into account during the back propagation and everything. So even though it's something that can be specified sort of manually, it's taken into account during the whole training process. So in this case, sine and cosine have no probability, so we're unable to sample those. So it's really a way of sort of pruning our search space to prevent things that we know a priori that we don't want. So here's some other examples of constraints that we can apply. One of them is that the length must fall between some pre-specified minimum and maximum. So for example, we can say that we don't have expressions that are less than length 4 because those are probably pretty trivial, or greater than length 30 because maybe we think that's too complicated for what we want, because we're trying to find a simple expression. Another example constraint is that each input variable must appear at least once. So say you have 5 different input variables for your problem, and you know that your response variable depends on all 5 of those. Well, then you would expect your expression to include all 5 of those. So that's something that you can do. And another one that's more pertinent in physics would be that you can constrain the selection process such that each operator and output follows its physical units. So if you have units attached to your input variables, you can constrain your search so that everything you sample is guaranteed to have those identical units. Again, these are things that are totally not doable with traditional genetic programming or evolutionary approaches. So now we have this RNN that we can sample expressions, or we can generate expressions randomly from it. And we can say that this defines a probability distribution over mathematical expressions, and we'll denote this distribution as pi. So the goal is to optimize pi so that we're producing better and better expressions, and we want to do this using a gradient-based approach. The problem is that the reward is not differentiable with respect to the RNN parameters. So the reward we're viewing as a black box. So we can't just do a supervised type setup and differentiate that directly. But we make an observation that the expectation of the reward, the expectation from samples of the distribution, is differentiable with respect to the parameters. That's probably also not obvious, but it's something that we can show theoretically. And because of this expectation of a reward is precisely the reinforcement learning objective. So our proposed solution is to use reinforcement learning. So we use, in particular, standard what's called policy gradients to optimize the expectation of the reward coming from samples from the distribution. And this has been done before in other contexts, like neural architecture search, where they use policy gradients to optimize neural network architectures. So we identified a key theoretical issue with these approaches, though, which is the following. So the objective function J here can be expressed in words very simply. You're trying to maximize the expectation of the reward under the policy. There's a problem with that, though. In regular RL, that's exactly what you want to do. You want a policy, say, a controller that plays Atari very well on average, or you want a chess player that plays chess well on average. And that's exactly what you get with these policy gradients. You're maximizing expected reward. But what we're solving is a slightly different problem. We're doing a discrete search problem. All we really care about is the very best that we ever get, the single best or maybe few best samples that we ever get from our policy. I just want the single best expression that fits my data. That's going to be my answer. I'll completely throw out the distribution. I'll throw away the RNN after that. So there's kind of an objective function mismatch there between what we're optimizing, which is expected reward, and what we actually care about, which is best case reward. So that's a big problem, because if you look on the right, this is a sketch of several different distributions of reward. So we have some policy, and that policy, if you sample from it a bunch of times, induces some distribution over rewards. And these three different colors, the black, blue, and red curves, they all have the same expectation. So to our loss function, they all look the same, but they're very different in terms of what the best case rewards would look like. So even though they have the same expectation, what we really care about is stuff over on the right that has the very high reward. So it gets even worse. So if you look on the right plots, for example, you have the blue curve, which has a better expectation than the black one. But actually, the black one is way better for our case, because it has much higher density on the right end of the highest reward expressions. So what we want to do is optimize for best case instead of average. So that's sort of the key methodological question that we're asking. How can we optimize for the best case performance instead of average performance? So to do that, we introduce something called risk-seeking policy gradients. So to introduce that, I'll first go over some details of the standard policy gradient, and then how we propose the risk-seeking and what's different there. So this is definitely the most sort of technical in the weeds slide. So after, I'll try to give a higher level explanation. So this is the standard policy gradient objective. We want to maximize expected reward. In words, we're maximizing the expectation of samples from the policy, which again is optimizing for average performance. So we can take the gradient of this expectation, and you're given this result right here. This is called the reinforced rule. It's also called a policy gradient. It's one of the key basic reinforcement learning strategies to optimize policies. And there's also a Monte Carlo approximation to this gradient, which is shown here. The reason sort of this theoretical result is important is because it lets us approximate this gradient in an unbiased way just by sampling from the policy and then computing rewards. So that's what lets us get to a practical algorithm. So that's all very old stuff that it has been used for this discrete optimization, but suffers from this expectation problem. So we propose a slightly different learning objective. Our objective is still an expectation. We still want to maximize expected reward, but we can transform it into a conditional expectation. We want to maximize expected reward conditioned on the reward falling greater than some R epsilon, which is a reward quantile of the distribution. So in other words, we want to maximize expectation of the top epsilon fraction of samples. And this is a way of maximizing for best case performance. So instead of maximizing all samples, we only care about sort of the upper tail of our distribution. So it turns out that you can still compute the gradient of this objective. And there's a couple differences that you'll note in red here between the standard policy gradient and this is our risk-seeking policy gradient. And similarly, we can come up with a Monte Carlo approximation for this policy gradient. So again, a lot of this is pretty deep in the weeds. So the main idea here is that this is the goal, sort of in symbols, maximizing expected reward conditioned on the reward being greater than some quantile. And this is just the goal in English. We want to maximize sort of the top end of our distribution, the best case. And this is our theoretical result, which of course makes reviewers happy, but more practically, what really matters is this practical result that says we can actually do this. We can estimate this gradient by just taking samples from our policy, evaluating those samples, and then moving in the direction of this gradient. So let's put it all together now, and we come up with what's actually a pretty simple and straightforward algorithm. So we take our recurrent neural network, and we sample it n times. We sample a batch of n expressions according to the procedure a few slides ago. So now we have a batch of these expressions. They're all completely different length, shape, and all of that. And then we evaluate each expression by computing the rewards. Let's say the rewards are bounded between 0 and 1. So we have some good stuff and we have some bad stuff. From there, we can estimate the quantile just using the empirical quantile. We sort them and chop off say if epsilon is 0.1, then we chop off the bottom 90%. And then we filter these. So we just keep the top epsilon percentile of our samples. Now we train on this batch, but we're only training on the filtered batch. The regular policy gradient would have just trained on the entire batch. But here, really the only difference is that we train on this filtered batch. So practically, it's pretty simple. You take the standard approach, but you only train on the good stuff instead of training on everything. And by only training on the good stuff, essentially your network is going to learn to only optimize for those good things, or that best case scenario. So as an aside, I wanted to, something is going on with the slide. Just as an aside, I wanted to ask the question, is this really reinforcement learning? It doesn't really sound like it in a lot of senses. So this figure on the left is probably something you've seen before, where you have sort of the quintessential reinforcement learning loop. You have some environment, could be Atari or some video game, for example, that's producing these observations, say pixel images. And these observations are passed to a reinforcement learning agent that selects an action, up, down, left, right, for example, in Atari. And that action is sent back to the environment to give a new observation and a reward, which is the game score for that step. And this is sort of the RL loop, and you're trying to optimize your policy so that it's picking good actions that give you good scores. That's sort of the traditional control problem. So what we're talking about here, it seems wildly different in a lot of ways. It seems like discrete sequence optimization. That's what it is. But then I'm telling you that we're optimizing it with reinforcement learning. So there's a bit of a disconnect. In fact, when I first started researching this approach, for a moment there, I was actually kind of staunchly opposed to calling it reinforcement learning because it doesn't really have the flavor in a lot of senses. But I've gone back and forth a lot in that thinking, and I'll say this is that it's perfectly accurate to call it a reinforcement learning problem, but it's not necessarily helpful to think about it as an RL problem. But just to demonstrate, I'll show you how you can take these components: policy, action, environment, observation, reward, and sort of fill in the blanks to describe how it is an RL problem. So the policy is really our recurrent neural network, our sequence generator, and the actions would be these individual tokens. And the observations would be the parent and sibling of the previous tokens. And in this case, the environment is really nothing special. It's just sort of the thing that strings them all together in this tree-like thing. And then we get a reward. One difference is that here we only get a reward at the very end after the whole sequence has been selected. Otherwise, you can just view it as a reward is always 0 until there's a terminal reward at the end. So that's one difference. But you can still sort of you can give exact mappings to all these pieces of reinforcement learning and show that it really can be viewed as a reinforcement learning problem. And the main reason I would say it's reinforcement learning is because we're still using the same RL objective, which is this expectation of reward, and we're using policy gradients to get us there. But I would also say that it's not really very helpful to think about it as an RL problem in a lot of ways, because we don't have a lot of things like credit assignment, or there's not really a temporal aspect that most people associate with reinforcement learning. So that's just an aside. It took me a long time to sort of frame my mind around this being RL and if it was truly RL or not. So we'll go back to the algorithm, and here you can see the algorithm sort of in action. So these blue dots are the training data. So this is the data we're trying to fit, and the red dotted line is the underlying ground truth expression that the data was generated from. Of course, we don't actually get to see this expression. So when I click start, what you're going to see is a ton of different expressions, and every frame is a plot of the batch of expressions at that iteration. So you're just going to see a ton of different expressions changing over time. So I'll start the video, and you can see at first everything's all over the place. It hasn't learned anything, and over time it starts to learn, starts to connect the dots a little bit better. And by the end of training, it converges and it finds pretty much only good-looking expressions, including it finds the ground truth expression with a fairly high probability. So now we'll show some results with our setup. So the experimental setup is that we take a benchmark problem. So in symbolic regression, what a benchmark looks like is a ground truth expression that you generate data from, and you may or may not add noise to it. And then the goal is to then recover that expression. You hide it from the algorithm and you try to recover it. But the reason that's nice is because there's this very clean binary. You either got the problem right or you didn't. It's this needle in a haystack problem, and you solve it by getting the global optimum, something that's exactly symbolically equivalent. And we compare against a bunch of different baseline algorithms. I won't get into the details of all of them, but in particular, priority queue training is another method, a deep learning-based method that is trying to solve this expectation problem. But they have a key limitation there, which is that their approach only applies to problems where the reward function is deterministic. If you try to add just random noise to the reward function, PQT just completely breaks down. Whereas the risk-seeking policy gradient, since we're still dealing with expectations, is perfectly fine. It works for any single RL environment. The other one, which is in gold here, is Eureqa. This is really known as the gold standard for symbolic regression. It's commercial software that requires a license that's based on some evolutionary type approaches. And this is widely used commercial software that's been around for a while. And here we show the results. So there's 12 different benchmark problems that we try. And in the second column, you can see the corresponding ground truth expression that we're trying to recover. And you can see that our method, deep symbolic regression, or DSR, is outperforming even this Eureqa, this gold standard symbolic regression baseline. So there's kind of another neat benefit of this approach, which is that we get a lot of generalization sort of for free just by virtue of working with symbolic expressions. So for example, let's consider the task of predicting the series of harmonic numbers. So harmonic numbers is just the sum of the first n reciprocals. And let's say we train on the first 50 harmonic numbers. We run our algorithm on these data points in red, and we run a multi-layer perceptron or a small neural network on these same data points. And not surprisingly, both of them fit the data quite well. Okay, well, what happens though if we start to extrapolate? So we move the data beyond the training regime, well into values that we never trained on. We train on the first 50 and evaluate that up to say the first 5, 6, 700. And we see that the multi-layer perceptron, not very surprisingly, just plateaus at some point and starts picking the same value. So it extrapolates very poorly. Whereas the expression that we came up with, which is shown here, actually seems to extrapolate quite well for all real numbers. And it turns out that even though we don't know, there's no closed form for the series of harmonic numbers, we can show theoretically that our error is actually bounded by 1/1,000,000% for all real numbers. So we extrapolate to infinity under 1/1,000,000%. And again, while it's not, there's no analytical solution, you can do a Taylor expansion of the series of harmonic numbers, and which is the first three terms look like this, which actually match the same terms as we found. And another really cool thing is that you have this constant that pops up. This constant gamma is known as the Euler-Mascheroni constant, and it was discovered by Euler in the 18th century, and it just sort of popped up out of nowhere to, I think, five or six decimals in our approach. So here we just wrote it as gamma, but really gamma was not part of our library or anything. It just found that constant and used it, and it matches the same one that's known in the Taylor approximation for the harmonic series. So this is just a cool little story to show how working with expressions has some real benefits in terms of generalization and learning something underlying about your data. So here I wanted to summarize the risk-seeking policy gradients. So we have, I'll play this video and you can see in red is the standard policy gradient. This is across training. So you can see the distribution of reward is sort of shifting to the right, which is what you'd expect. Standard policy gradient is optimizing the expectations, so you just kind of get a shift to the right. Whereas this risk-seeking policy gradient, we're optimizing only the best case. So instead, I'll play the video again. Instead, you kind of see the blue distribution. It's not really shifting to the right so much as the right shoulder is sort of being pulled to the right. So very early on, you get this high density around 1.0, which is by the way, a perfect answer. So it solves it early on. So the distribution is pulled to the right. So you get a lot of weight on the right-hand side. But you can also see that that comes at the expense of you actually get a lower worst case reward. So you actually even sometimes have a peak around 0, and you get a lower average, which is denoted by these blue and red circles. So the benefits of this approach is that it works for any RL environment, not just these deterministic tasks. So the rewards and even the transition dynamics can be stochastic. You can also combine it with other policy gradient techniques like control variates, proximal policy optimization, or generalized advantage estimation, which are all three huge in the field of RL. And there's other applications too. So of course, we've talked about several other discrete sequence optimization tasks like antibodies or neural architecture search. But you could also use it in the traditional reinforcement learning task. For example, let's say you wanted to achieve a new high score in Atari. So normally, again, these DRL algorithms are trained to produce a policy that produces a good score on average. But let's say that you were evaluated by playing 100 episodes of your game and reporting just the top one. Well, in that case, you want to behave in a risky or thrill-seeking way, which is precisely what our risk-seeking policy gradient does. Also, if you want to sort of win a tournament and you're in an underdog situation, instead of just kind of acting well on average, you might want to take some risks to improve your probability of actually winning the entire tournament. So lastly, I wanted to talk about a new application where we take what's essentially the same approach, but we swap out the black box. So our framework treats this reward function as a black box. By black box, I mean that we're not taking any gradients from it, which means we can swap it from one thing to another to solve a different problem. So what's another problem we can solve? Well, one interesting one is, let's look at, this is the standard reinforcement learning loop again. But now let's say that we want our policy to be a short expression instead of a neural network. So in other words, we want to get an interpretable RL policy. We want to play these video games with equations, with small tractable mathematical equations. So how do we do that with our approach? Well, it's actually really easy. You just take this left-hand figure, you put a box around it, and you call that our black box. So you kind of get this inception-like or RLception loop within a loop approach going. So the idea now is that we're generating these sequences, these expressions, and the way that we evaluate an expression, instead of fitting it to data like regression, we take the expression and then we use that expression directly as a policy and play, say, 100 rounds of the video game using that expression policy and compute the average reward of playing that game. And that's the reward that we send to our RNN. So you have sort of this outer RL loop where you're trying to optimize the expression, and an inner RL loop, which is evaluating how good the expression is. And so we tried that, and it's pretty cool. You come up with these expressions that are playing your game. So on the left and right here are two very common benchmarks. On the left is lunar lander, on the right is hopper. And traditionally, these are high-dimensional continuous control problems that are controlled using deep reinforcement learning methods, where the policy is represented as a neural network. Here, we use our method and our policy. You can see, you can look at it here, you can read it, you can understand it. It's just a short expression. And you watch it, and they play the game quite well. So we're playing lunar lander with the expressions, or learning to hop around on one foot just with expressions. So here's some other results. So using those expressions, we have these expression-based or symbolic policies. It's not surprising that they're simpler or more interpretable, or they're cheaply deployable, things like that. That's really not that surprising. So you can see the complexity on the left. The left two are our symbolic policies. This is sort of a attempt of a low-dimensional representation of plotting our policy. And on the right is the neural network, and it kind of looks like a Rorschach picture or something. It's very complicated. There's lots of little details. You change one state variable, and then your policy gives you a completely different action, whereas the symbolic ones are very, very simple. So of course, there's a big difference in complexity, and you might expect that this would come at the cost of maybe lower performance. And that's exactly what we expected, but it turns out that's not really true. So we actually found that these tiny little expressions are actually outperforming entire neural networks using state-of-the-art DRL algorithms. So there's a neat little repository called Zoo that contains pre-trained neural networks that have been highly tuned for each algorithm, each of these algorithms in each RL environment. And we took all of these pre-trained ones and evaluated them and just compared them to our expression policies, and we're actually beating them. So it's it was very much unexpected. We thought that there'd sort of be this trade-off between all the benefits of a symbolic policy, things like interpretability, deployability, that there would be some trade-off with performance, but it turns out we sort of got the best of both worlds here. So that was a very exciting result that I think we've got another week till we find out our final decision, but it's looking good. And then with the last few minutes, I wanted to show a demo of our approach on the regression task. So let's see if I can switch over quickly to share my screen. So we have this, it's a web-based demo that we can run our approach on. So it's similar to something like TensorBoard, where you just, you start it up in a terminal and then you just head to a local URL address and you can play around with it. So here's the UI of the demo. Hopefully it's coming clear through the video. So the first thing you do is select some data. So you can either give it a CSV, or in this case, we just have some benchmark data sets you can look at. So here's one of them. Here's a 2D data set. You can look at the points. We'll play around with this one, number 6. And then you set some config parameters, just sort of use the default. And here you can adjust, things like hyperparameters and all of that. And so again, these blue dots are the data. So I'm going to hit start over here, and then in real time. So this is actually running on my computer. Let's hope it works. And you'll see the plots of the best expressions popping up. So I hit start, and you see here's the first sort of okay expression that it finds. It looks a little bit long and ugly. It has a fitness of 0.828 instead of 1.0 is the highest that you can get. And within this demo, you can also click on a particular expression and find out more about it. So here we can see a LaTeX rendering of the expression. We can also look at the traversal itself. It's very long and complicated in this case. And we can also interact with things a bit, like let's take this one. It has these weird spikes and stuff, so let's ignore it. Let's hide that expression. I'll just zoom into the actual data we have, and let me keep running it again. So again, now it's still running in real time on the right, and on the right you can also see some diagnostics of the training happening. So you can see training curves for example. You can see the distribution of rewards shifting to the right over time. Here's a plot of the complexity of the expressions, and we go back. Oh, actually, there you go. 1.0, it actually already found it. So sometimes it's a little too good. It doesn't give you time to see things. So it got, this is the benchmark, sine x plus sine of x squared plus x. So it find the exact solution in this case. You can see the traversal is a lot smaller here, and here's the LaTeX representation. Even though it got the right answer, I think, yeah, it's still running. So we can still kind of see the distribution shifting to the right. The other really cool thing about this, so this task of creating a demo platform started off as just like kind of an eye candy, like this will be fun for people to visualize it. But then we realized that actually it's becoming a pretty indispensable tool for real world applications. And the reason is because we can interact with this demo. It's not just a visualization platform, it's an interactive visualization platform. So for example, we can change hyperparameters. Let's bump up the learning rate, and decrease the batch size, for example, and we can do that all in real time. And on top of that, you can even sort of add your own biases. So let's say you're looking at things and you think exponent is maybe not a great fit, so we can actually tune it down, which adds a prior to the sampling process, so that sampling exponent has lower probability. And let's say this looks like a sine wave, so let's turn sine up and let's turn cosine up. And that's all done in real time. So it allows the humans to incorporate their own thoughts and knowledge into the search process. So we can also look at things like the priority queue. The priority queue is sort of the top. It's a list of the top expressions that have been found so far, and we can actually identify individual expressions in that queue and tell the algorithm to either include it in the queue or block it from the queue, which is sort of in addition to the loss function that tells us, find stuff more like this or find stuff less like this. So it's slightly different than the reinforcement learning objective, but that's something else we can do. In this case, you see the correct answer several times because it found it with slightly different variations on the traversal. Yeah, so again, it's kind of funny because this started really as just a hey, let's make a flashy little visualization, and now it's turned into be something that's pretty critical because it lets us interact with the platform in real time, and it lets the human incorporate some of their own knowledge into it. So let me go back to the slides. So just to conclude, deep symbolic regression is a method for the very general discrete sequence optimization problem that's using deep reinforcement learning. We've shown its application to symbolic regression has been extremely successful, and we're starting to apply this technology to other problems like the interpretable RL, where we show the expressions playing games, and also an antibody design problem. From my perspective, the two major advantages of this approach is one, this risk-seeking training, which is unlike standard approaches that are optimizing for expected reward, we're optimizing for best case, which is what we really care about. And also the ability to incorporate domain knowledge via these priors and constraints is very, very powerful. We're every week we're coming up with some new new prior or something that we want to incorporate into the problem, and it's really easy to encode. And again, that's something that it's possible because we're generating these sequences or these discrete objects sequentially, whereas other approaches like evolutionary approaches just sort of spit out entire objects at once. So it's very difficult to make those objects adhere to a bunch of constraints that you apply. For future work, we're working on some hybrid methods where we have reinforcement learning spitting out expressions, and then the batch of those are sort of fine-tuned via genetic programming or evolutionary approach, and then they're sent back to the reinforcement learning as off-policy samples. And it turns out that improves things quite a bit. We also have a couple workshop papers that we're presenting on various ways to improve the ability to explore in this symbolic space. Again, sometimes the size of the search space is more than the number of atoms in the universe. So exploration is really key to success. And just as a bibliography, this is the name of the ICLR paper that we'll be presenting this year. So yeah, thank you everyone. Thanks so much. I'm happy to take any questions. Jim Leak asks, how can we try out your stuff? Well, we have an open source version of the code. Actually, let me find it. I can just paste. Oh, actually, I don't know that people can see. Can people see the Q&A?
I think everyone can see all the questions.
Okay, that's fine. Then.
I don't know, Jen, can you confirm if everyone can see the questions? We're not sure.
I don't believe people can see the questions.
Okay. So can you pull up the website or something so everyone can see it?
Yeah, so we did a code release internally for our method. So it's just a GitHub page. If you search GitHub deep symbolic regression, you'll find it there. But here's a link. I don't know if you can see the URL.
Yeah, we can see the URL. Can't copy it, unfortunately, but I guess everyone's saying that they can't see the questions and we don't have the chat activated at this time. So if you're interested, we'll give you a couple of minutes to take a look at that URL. And
again, if you just Google GitHub deep symbolic regression, it should be the first one to pop up.
It's a good thing we covered this. I think that's actually a lot of the questions.
Okay, good.
Can we use this really cool stuff?
Yeah, so I have to unshare again to go back to the questions. Let's see. So Kayla is asking, how can we deal with expressions that say powers of non-integers? So example, x to the 1.5. and how would that be translated into a tree or sequence? So that's a good question. It really depends on what your library is. So if you noticed, I didn't even have the power operator wasn't a token in these benchmark problems that we were doing. So if you want to do powers, then you can do it a little bit tricky with mixing up exponents and logs and using tricks there. But it just depends on what your library is. If you think power should be part of your library, then you can add them, and you can add. You can also add. I didn't really talk about this, but you can add a constant token that's sort of an arbitrary constant. It's not attached to a specific value, and then as an inner loop, you can use something very simple like scipy dot optimize to optimize the constants of that expression. So, for example, my expression might be sine of constant times x, and those are the tokens. Constant is just a token. It's not attached to a floating point value. But then when I compute the reward, I do an inner optimization loop where I try out different values of the constant, and I optimize the constant and say it's 3, so or 3.1. So sine of 3.1x would be the final expression, and then the reward's based on that best fitting one. So if you wanted something like x to the 1.5, then it would be as simple as power x constant, and then the constant can be optimized. Someone asked how this performs on noisy data. Yeah, that's a really good question. So I didn't show it there. The table that I showed is on noiseless data, but you can take a look at the paper. We try a couple things. One thing is you can increase the noise level, and then of course what happens is the recovery rate will drop. But what's kind of funny is that the reason it drops is because then you can actually get sort of incorrect answers that actually fit the data a little bit better. So it's kind of a weird form of overfitting. Overfitting is actually still a thing, even in symbolic regression. Just kind of takes on a different form than you're probably used to for regular regression. But in general, we're still outperforming all of the baselines, including Eureqa and the other DRL-based ones, adding different levels of noise. Also, that sort of performance degradation as noise increases changes based on how many data points you have. So in the limit of infinite data, then the noise doesn't actually really mean anything, because it's just sort of changing the reward landscape. Someone asked about performance on discontinuous functions. I would say, so I don't know that I explicitly mentioned this, but when you have a benchmark problem, it's not just the data. The benchmark problem is also defined with respect to a fixed library. So one of our benchmark problems was square root of x. Well, that's a really easy problem if square root is in your library, but it wasn't. So we had to get there through some funky exponents and logs tricks to get there. So I would say that if you have discontinuous functions, then you would have to add discontinuous operators like step functions into your library. And so that's something that, conceptually it sounds a lot different, but it's all it means is that having more interesting tokens that aren't just like sine, cosine. In this case, you could have a step function would be like an if then else operator. It'd be like a ternary operator where you have a condition and a value if true, a value if false. And that's an example of how you can get stepwise functions. Or if your entire library is comprised of tokens that look like that, all of a sudden you've moved toward decision tree search instead of continuous expression. So actually, as another follow-on work, we're searching the space of decision trees for other problems, for example. So someone asked again about things like x to the 1/3. You can either get that just by doing this inner constant optimization, or you can it can just naturally get it by, the power. And even if you don't have integer tokens in your library, you can say, x divided by x plus x plus x is a really inefficient way to get a 1/3. But if you really want it, that's one way you can get it. But I would say that for more realistic problems, you would just add, you could either add the cube root operator directly, or if you didn't know a priori that you'd get cube root, then I would just add the constant the constant operator, and again you have this inner optimization loop. The demo and config file available for download. Yeah, that's part of the GitHub. Someone asked again about the error. Yeah, and again, if you take a look at the paper, the paper should be linked on the GitHub as well. There are some data sets that have different levels of noise, and we tested against all of that as well. Someone asked about the 12th benchmark, which if you notice, everyone gets 0%. it doesn't look that, I can pull it up. It doesn't really look that bad in some ways. Let me share PowerPoint again. Yeah, so if you see this UN12 benchmark at the very bottom, everybody gets 0%. And if you look at it, though, it doesn't really look that bad. It's just, it's just a polynomial. It's two variables, but that doesn't really make things too much harder. It's been really puzzling. I think it's actually a combination of, this doesn't really tell the whole story. If it depends a lot, for example, on the domain. So the domain for this problem is that x and y are between 0 and 1. And if you plot this function and you sort of zoom out, then there's a lot of signal. There's a lot of ups and downs. So it's pretty easy. We've tried that. If you move it to like minus 10, 10, you can get it. But on actually, I forget if it's 0, 1, or I think it's just on 0, 1. That function looks like an inverted top hat that's curved. It's a funky function. And yeah, I think it's partially just because the domain is very restricted. So there's just very little signal to learn from there. Also, there's other little things like this 1/2 is difficult to get. So again, these benchmarks are tied to specific libraries. So we didn't decide them. They're a benchmark. They're part of the description of the benchmark. And this library, it doesn't have integers at all. So actually, in order to get the 1/2, you have to do something really awkward, like multiply the y squared by x divided by x plus x, which is just kind of a very inefficient way, and it makes it makes your expression a lot longer. So it's very difficult to find that. So that's another reason. So if we got rid of that 1/2 again, that's it becomes easy to solve. So it's kind of one of those things where it looks a little bit alarming, because it's like, oh well, if you can't find that, how are you going to find a real world problem? But again, it's really just because of the way that the problem was set up. It was intentionally made hard by having that small domain and not giving us things like constants or integers as part of the library. As soon as we do anything like that, we can start getting it. Someone asked, is there an example of the constant optimization? You can look at the paper there. It can also be done in the demo as well. It's just it slows things down quite a bit, because all of a sudden the constant optimizer becomes the limiting factor in that. Ignacio asked a really cool question. Can you feed the mean squared error at intermediate sampling? For example, like halfway through sampling an expression, there's still information there. So he's asking if we can use those to get sort of the best possible mean squared error that could provide hints as sampling goes forward. So in other words, can we leverage any semantic information or mean squared error based information as we're sampling? That's a really, really interesting question. I think that there's definitely things you can do there. It's not something we've explored directly. I used to say this, which is that I would say, the reason we only get this terminal reward is because an expression is a thing. It's concrete, but half an expression is meaningless. It doesn't. You can't do anything with it. But that's not entirely true, because, for example, if the root node is sine, well, then you know that the bounds of your expression. Everything is below sine, you know that you're bounded between plus and minus 1. So you can use that type of information to help guide the search. That's not something that we've done yet, but in principle, yeah, I believe that there is. And then another great question from Ignacio: is there anything that can be done to prevent sampling equivalent expressions? That is a really interesting question that we're just addressing now. So a good example would be, A plus B versus B plus A, or A plus B plus 0, where 0 can come in all sorts of forms, or A plus B times 1, where 1 can come in all sorts of forms. And is there a way that we can sort of prevent us from doing that? So, the problem you might call is needle in a haystack, but really it's needles in a haystack, where the needles are these different versions of the same symbolically equivalent expressions that we're trying to find. All we need to do is find one of these needles. But one thing that we can do to help would be to constrain the search such that we're only looking for a particular class. So there's something called an equivalence class, and equivalence class is a very generic term, but we can define what's called a semantic equivalence class, which is basically the entire class of, all forms of A plus B. So that could be B plus A times 1 plus B minus 0, all of that stuff. And I don't think it's possible to simply add a constraint that says, only search for one sort of canonical member of that equivalence class. But I think there's a lot of things we can do to get there. For example, one thing that we're trying now is applying a constraint that essentially gives some lexicographical ordering to the tokens. So for this would be only for binary operators that are cumulative, so plus or multiply. You can swap the children and it doesn't make a difference. And so in that case, we can say, we can just apply some arbitrary ordering, lexicographical ordering. And for the left child, you can pick whatever you want. And the right child, you can't pick anything that came before that in the dictionary. So in other words, that would be a way of making it so that you'll never be able to sample B plus A. You can only sample A plus B. So that's one, but it's a wide open question. And that's just sort of one way that we can get there, that is dealing with specifically the plus and the multiply operators, because they're these binary commutative operators. There's a couple other questions. I know we're running out of time here. One of them is, what type of RNN? It's just a quick answer. We use the LSTM. In general, we can use any sort of types. We can't use like transformer, for example, because it's not actually an RNN. It's like a many-to-many mapping. And we're doing this autoregressive or sequential sampling where we have to do one token at a time. We don't know the whole input sequence up front. So that precludes us from doing something like a transformer. And then we have a question: what are some examples of real-world applications? So, of course, as a lab project, we get to focus a lot on the methods here, which is fun, but we're also tied to some real applications. So to date, we've been focusing on physics problems where essentially the story has been a physicist has, as part of their grad school or whatever, is tasked with, coming up with some equations that explain some data. So we have one example that we've been working with outside collaborators on physics wrinkling data. So you have, for example, in apple is made of, a core, it has the sort of the flesh, which is one substrate, and then it has the skin around it, which is a different substrate. You put that out in the sun, and because you have these substrates attached, you get sort of this wrinkling pattern there. And it turns out that the properties of the wrinkling, like the period and the amplitude, are a function of things like the different Young's moduli between the two materials and the temperature and all sorts of stuff. And that's sort of a whole field of wrinkling on thin films. And we are working with someone who, as part of their graduate studies, did lots of experiments and tried just, pen and paper coming up with equations that would fit that data. And, we do know the right answer in this case because, that grad student graduated. And now we're trying to take our approach and see if we can sort of recapitulate that process. So it's kind of the idea of like, we're not trying to replace the grad student, but we would love for the grad student to use this framework as a supplement to their methods as they, try to graduate by coming up with expressions that explain their data.
And it looks like we have two more questions, one here and one in the chat, and then we'll go ahead and cut everybody off because it sounds like everyone's very interested, but of course, Brendan will be happy to talk offline. So do you see the last one in there?
Oh, yeah, I see. Yeah, so the question is, do density results, such as polynomials being dense in the space of continuous functions, inform the selection of available tokens? So I think the token selection is probably the part that's the least automated. Right now, the token selection is pretty much something that's set a priori by the user. In the demo, you can see that you can turn on and off tokens. So the user can do that. You can still do that in an online way, but it's not something, we're currently not looking at ways that sort of try to inform the token set before you actually initiate the search process. But there are some methods that do that. For example, like in a supervised way, you take a data set and just in a purely supervised way, you just try to learn what's the outermost operator of the underlying function describing that data. And you can do studies like that, or you can do it. It could be a a multi-categorical task where you're trying to predict all the different tokens in a data set, but in a purely supervised way. And then you could use that, to sort of seed in the discrete search. You can, for GSR, you can use that to seed what the starting tokens should be. But again, I mean, today we've mostly been working with these benchmark problems where they just sort of give you a list of tokens that you're allowed to use for that problem.
And very last question from the chat, which is apparently actually active, and I did put the GitHub link in there if anyone can see it and is interested. So last question, what are ways you're considering for improving exploration?
Yeah, that's a good question. So one of them in particular is there's something I didn't really have much time to talk about, but there's this, in reinforcement learning, you typically give an entropy bonus. When you have these stochastic policies, you promote exploration by increasing the entropy of that distribution. So in this case, we have categorical distribution. So it looks like a bar plot. And that's high entropy when it's close to uniform. And that's low entropy when it's very spiky. And so if it's very spiky, then it means it has high confidence in one particular token. But to induce it to explore, you give sort of a bonus to the entropy. So that encourages it to get closer to uniform, so that it's also exploring other exploring around that token. So that's something that's very standard, this idea of an entropy bonus. But in this case of discrete optimization, where it's really a sort of a search, where the search space can be viewed as sort of a tree, whereas it's combinatorial explosion. So that what ends up happening is that the entropy bonus, it ends up being satisfied by the earliest tokens. So in other words, it's really easy to get high entropy in the tokens that come at the end. So the entropy bonus just does it like that by having really low entropy in the beginning and high entropy at the end. So what we did is we added which we're calling a hierarchical entropy bonus, which is where we sort of increase the size of the bonus according to where you're at in the tree. So in other words, we tune the entropy bonus to be a lot higher earlier on to sort of force it to explore. Otherwise, it's really only sort of exploring like certain subsections of the search space. So that's another paper that we have at a workshop on hierarchical entropy bonus.